Hi dear students, welcome to today's online class. Today we begin the first module of organic chemistry paper for 6th semester, that is structure elucidation using spectral data. This module deals with the application of various molecular spectroscopic techniques which you have learned in 5th semester. Mainly we focus on 3 spectroscopic techniques, that is UV visible or electronic spectroscopy, number 2 infrared or vibrational spectroscopy, and number 3 nuclear magnetic resonance spectroscopy or NMR. In this class we discuss the introduction of UV visible electronic spectroscopy. The most important application of any molecular spectroscopic technique is to elucidate the structure of various organic molecules. What is meant by spectroscopy? Spectroscopy deals with interaction of electromagnetic radiation with matter or molecules, and it involves, in any spectroscopic technique you can see that it involves transition of a molecule from lower energy level to higher energy level. For example, suppose there are 2 energy levels, E1 and E2. This is the ground energy level and this is the excited energy level. It can be of various types of energy levels like electronic energy, vibrational, rotational, etc. Molecule will be normally in the ground state. And when we provide some radiation, it will absorb certain wavelength and go to the excited state. And this energy gap delta E, according to Planck's equation or according to quantum theory, energy is quantized, so it is equal to h nu or is equal to hc by lambda. That means for transition to occur, we need an electromagnetic radiation of a particular frequency or wavelength. Now, based on this energy gap, the wavelength will vary. So, for various types of transitions like electronic, rotational, vibrational, etc., a molecule need different types of electromagnetic radiations having different wavelength. Here, for electronic transition, a molecule require UV or visible radiation because the energy gap between 2 electronic level corresponds to the wavelength or frequency of UV visible radiation. Now, coming to the electronic spectroscopy, you might have learned about the basic principles. I just make a recap of all this. In a molecule, first of all, let us discuss what is the range of this radiation, UV visible radiation, used for this study. When we take electromagnetic spectrum, you can see with the visible light, that is VIBGR, that is a visible range, and the radiation, the part having wavelength less than violet is called UV, ultraviolet, UV, which is of 2 parts, that is, one is near UV, that is near UV, which is close to violet, and this is called far UV, or it is also known as vacuum UV for some reason, vacuum UV. Now what about the values, the wavelength? See, the range is from 10 nanometer to 800 nanometer used for this UV visible spectroscopy. So far UV ranges from 10 to 200 nanometer. Okay, and near UV from 200 to 400, and visible range, as you know, is ranging from 400 to roughly 800 nanometer. So molecule can absorb the radiation of a particular wavelength in this range. That depends upon the energy gap. Smaller the energy, you can see that according to Planck's equation, smaller the energy, delta E is equal to hc by lambda. See, for convenience, in electronic spectroscopy, we represent the radiation in terms of wavelength in nanometer. So, smaller the energy, larger the wavelength, right? So, when energy gap decreases, the absorption will move to larger wavelength. Remember that. Now, coming to types of transitions. What are the various types of transitions which is seen in electron spectroscopy? See, according to molecular orbital theory, we can see that there are mainly three types of molecular orbitals, as you know. One is sigma MO, pi MO, and what is N? N is non-bonding. That means you can see certain lone pairs in certain molecules. For example, if you take aldehyde or ketone which contain oxygen, which will have a lone pair. These electrons are present in non-bonding orbitals which do not take part in this LCAO mixing of orbitals. So this is N, non-bonding orbital which contain the lone pairs. Pi molecular orbitals, that is a pi bond, and this sigma molecular orbitals which contain sigma electrons. Naturally, there will be pi star anti-bonding orbital for pi, and for sigma there will be sigma star. So there are 5 molecular orbitals, of which these are bonding, these two are bonding, right? These two are bonding orbitals, these are anti-bonding molecular orbital, and this is a non-bonding orbital. Now, when we consider the types of transitions, so this is finished. What are the various types of transitions possible in electronic spectroscopy? Electrons move from lower molecular orbital to higher molecular orbital. It is from bonding to anti-bonding, or it can be from non-bonding to anti-bonding also. So, transition can be from sigma, pi or N to pi star and sigma star. So, considering various transitions, let us note the transition having maximum energy is from sigma to sigma star. Okay, this is sigma to sigma star transition. Okay, the next one, it can be from sigma to pi star, right? Or from pi to sigma star, which are having roughly the same energy. So this is sigma to pi star. This is from pi to sigma star. So 3 transitions are over. Now these transitions are generally having high energy, and it comes below 200 nanometer. Okay. Energy is large energy gap. When delta E is large, lambda will be small. So wavelength is less. That means it is coming in the far UV, which is also known as vacuum UV. Why the name vacuum UV? Vacuum UV. This range, that is 10 to 200 nanometers, is known as vacuum UV range. Why it is called so? It is because, see, molecules in air like oxygen, nitrogen, they absorb this range of radiation. Their electronic transition corresponds to absorption of UV radiation below 200. That means air molecules exhibit UV absorption below 200. So what? So when you are studying a molecule which is also having UV absorption below 200, you will have to evacuate the instrument, that is spectrometer, has to be evacuated to avoid the overlapping. Otherwise, it will show the absorption peak of nitrogen and oxygen also. So, spectrometer need to be evacuated to study molecules which are having absorption below 200. Because of that, this range is also called vacuum UV. Due to these difficulties, this range is of no interest. Normally, in studies, one is interested in other transitions which come above 200. Let us take the remaining transitions. Which are they? The next decrease, we are considering energy decreasing order. So it can be now next one, N to sigma star. Okay, this is next transition, N to sigma star. Then we can consider pi to pi star. Okay, this is pi to pi star. And finally, it is N to pi star. You can see that in all transitions, electron is moving to one of the anti-bonding orbital. It can be from bonding MOs or the non-bonding molecular orbital. So this is N to pi star. Now a question, which is having lowest energy transition? N to pi star. Which transition is having highest energy? Sigma to sigma star. Now, these transitions, these three, which are important in spectroscopic techniques, which comes above 200, that is 200 to 800 nanometer. Okay, so this is of importance or interest for spectroscopic analysts. Okay, and in this one we will be concerned mostly with pi to pi star and N to pi star. These two transitions are of maximum importance in studies. We will be more referring to these transitions in coming classes. Now transitions can be divided again into another way based on whether it is forbidden or allowed. In spectroscopy, you might have learned that it involves transition of molecule from lower energy level to higher energy level by absorbing radiation of suitable frequency, and which is governed by quantum mechanical selection rules, right? You might have learned about selection rules, which is coming from quantum mechanics. So here, pi to pi star transition is called allowed transition. That means it is symmetry allowed according to selection rule. Symmetry allowed transition, what does it mean? Both orbital has the same symmetry, both are pi. So pi to pi star, similarly sigma to sigma star, these two transitions are only allowed transitions. Whereas all other transitions like N to pi star, N to sigma star, pi to sigma star and sigma to pi star, all these are symmetry forbidden, because the symmetry of the two orbitals are not same. Now what is the difference between these two types of transitions? Allowed transitions will be very intense. You get very intense peak in the spectrum, and forbidden transition will be very weak. You get a very weak spectrum. That's the difference. Okay. Now if we are arranging these transitions in the energy order, we can write the energy order of these transitions. It's very easy. Sigma to sigma star is having maximum energy gap, so minimum wavelength that comes in far UV, energy decreases too. Next comes sigma to pi star, which is almost similar to pi to sigma star. These two energies are more or less same, decreases too. Next comes which one? N to sigma star, then pi to pi star, then N to pi star. Okay, this is the energy order of various transition. This order is important, right? cite some molecules as examples. Okay, we will consider the examples later on. We have a special session for that, discussing examples. Let us move on to the next point. Okay. Now, there are some terms involved, technical terms associated with electronic spectroscopy, like absorbance, molar absorptivity, epsilon, etc. This comes from an important law that is called Beer-Lampard's law, which you might have learned in 5th sum, which is mathematically represented as absorbance A, which is also called optical density, is equal to what? Log I0 by I. That is equal to epsilon CL. What are the terms? I0 is the intensity of the incident radiation. I is the intensity of the transmitted radiation. A is absorbance. Epsilon is a constant that's called molar absorptivity or molar extinction coefficient. C is the molar concentration, that is in moles per liter, of the solution which which contain the sample. L is the length of the solution. See, this is referring to an absorbing solution. Suppose you are taking a compound which is taken for this electronic spectroscopy, and you are taking it as a solution. Okay, you take the solution of a compound. For example, we are taking for example nitrobenzene to study, and it is taken as a solution. You will allow radiation to fall coming from UV visible range, and this is the intensity of the incident radiation. What happens? Part of the radiation will be absorbed by the molecule for their electronic transition, and the rest will be transmitted, and intensity will fall due to absorption, and this is the intensity of the transmitted radiation. Suppose this is the length of the solution or thickness of the solution, and concentration of the solution is C. So we have this equation, right? Now here the two terms, there is absorbance A and epsilon, molar absorptivity. You get familiar from this law, this equation. Absorbance is also called optical density. Epsilon is a constant for a given compound solvent combination, and it is also known as molar extinction coefficient. Now there is another term, that is transmittance, which is somewhat opposite of absorbance. That is T is equal to I by I0. But remember, absorbance is not I0 by I, but it is a logarithmic term, log I0 by I. So this is absorbance, this is transmittance, there is difference. So we can say that A is equal to minus log T, correct? There's a relation between absorbance and transmittance. Then, coming to lambda max and E max, the next term. See, let us see how an electronic spectra is plotted. It is plotted between lambda and intensity of absorption, which is represented using sometimes epsilon or absorbance or log epsilon, etc. This electronic spectra looks like this. You get a very broad peak, not very sharp. That's the speciality of an electronic spectra. Why it is broad? You might have learned it. It is because electronic transition is always accompanied with vibrational as well as rotational. Because, during electronic transition, this is ground electronic level, this is first excited electronic level. Each electronic level is further divided into vibration level. Each vibration level divided into rotation levels. So when there is electronic transition taking place, simultaneously there will be vibrational as well as rotational transition taking place. Due to that, the peak is quite broad, and there are some other reasons also. Anyway, now from this spectrum, the peak, we can note two values. One is this value. What is this? This is wavelength of absorption. The wavelength of the radiation absorbed by the molecule for transition. This is the wavelength at which maximum absorption. This corresponds to the peak of the curve. So this is known as lambda max. So for a molecule, when we mention its UV absorption, we will be mentioning this value, that is lambda max. Corresponding to lambda max, we can note a value here that is called E max. That is the intensity corresponding to lambda max, wavelength of maximum absorption. So these are two terms which are technically used in electronic spectroscopy or UV visible spectroscopy. Then the next terms, so we have discussed all these things, absorbance, these ones, and now what is Chromophranopsochrome? Again, this is a theoretical term which you might have learned. If you consider, for example, a molecule like nitrobenzene, okay, you know that nitrobenzene is having light yellow color. But if you take phenol, that is OH here, this is colorless. Pure phenol is colorless, but this is having a light yellow color. So here, the yellow color of nitrobenzene is mainly due to this NO2 group. It is mainly due to this nitro group. Okay. So groups like NO2, similarly aldehyde group, keto group, carboxylic acid COOH, nitrile, that is C triple bond N, SO3H, etc. These kinds of functional groups are called chromophore. Chrom means color. Color producing groups, in the sense they are having absorption well above 200 nanometer. These groups have got characteristic absorption above 200 nanometer, such that gives some color to the compound. They are called chromophore. What is the speciality of these groups? All these are containing multiple bonds, correct? Pi bond is there, so it will have pi to pi star transition. So chromophores are groups, those functional groups which are having characteristic absorption above 200 nanometer in UV visible spectroscopy. Whereas groups like OH group, and similarly OR, NH2, NHR, halogen X, etc. These groups, they do not have characteristic absorption above 200 nanometer, but when they come along with a chromophore, remember benzene itself is a chromophore because it contains double bond. So when the OH group comes along with benzene, you know there is a lone pair on oxygen, and on all these groups there is lone pair. So this is in conjugation, so the lone pair get delocalized into the ring. So the presence of lone pair on these groups increase conjugation, increase delocalization. That will increase the lambda max. So oxochromes, we can say color strengthening groups. These groups do not have characteristic absorption of their own about 200 nanometer, but when they come along with a chromophore, they will increase the lambda max, right? That is oxochrome. Now finally, we have to discuss about 4 technical terms associated with the change or shift in lambda max and E max. For that, let us consider again an electronic spectra like this, where we plot between lambda and epsilon. That's intensity and wavelength. And I have told you already that this value is called lambda max, that is wavelength of maximum absorption, and this value is called E max, that is intensity corresponding to lambda max. Now, due to various reasons like change in solvent, increase in conjugation, hydrogen bonding, etc., the lambda max and E max of a compound can vary, right? Then we make use of, when we use some operational terms, if lambda max of a compound increases, that means you are moving in this direction, right? Then it is called, that phenomena is called Batochromic Shift. Batochromic Shift. So what is Batochromic Shift? Change in lambda max to larger value. It is also known as the red shift. Why? In VIBGYOR, visible light, red is having largest wavelength. So increasing wavelength, to indicate that, we say red shift or Batochromic shift. If the lambda max of a molecule is decreasing, then the phenomena is known as, that is, you are moving in this direction. Lambda max is decreasing, it is known as Hipsochromic Shift. Hipsochromic Shift. It is also known as blue shift. We can put a simple example to understand this. Look at this. Benzene. Okay. Lambda max of benzene is found to be 255 nanometer. Okay. If you introduce an amino group on benzene, we have just learned that NH2 is an oxochrome. It has a lone pair in conjugation with the ring. So what happens? It will increase the delocalization, and that will increase lambda max. Lambda max of aniline is found to be 280 nanometer. See, it has increased. So this is a Batochromic shift. Interestingly, if you add some HCl, acid, to aniline, you know aniline is basic. If you add HCl to this, what happens? H plus get protonated on aniline group, NH2 group. It become anilinium ion, right? It become NH3 plus, correct? You understand? H plus attached on nitrogen using the lone pair, so it became NH3 plus. Interestingly, lambda max of this anilinium ion is found to be only 254 nanometer, more or less the same as benzene. Why? Because the lone pair has lost here, no more conjugation. What is this shift? This is called Hipsochromic shift or blue shift. Finally, if the Emax of a molecule is increasing, that means you're moving in this direction, it is known as Hyperchromic shift. Hyperchromic. Increasing Emax to a larger value. If the Emax of a molecule is decreasing, right? You are coming down. That phenomena is known as Hypochromic shift. These two terms are like what we use in our common as a common terminology, like in blood, when blood sugar is high, we say hyperglycemia, low hypoglycemia. If blood pressure is higher, hypertension, hypo, this is a common usage. So these are four operational terms in connection with change in lambda max and Emax. So that's all a recap of the basic idea, the basic concepts related to electronic spectroscopy. Using these ideas, we can go to application in the coming classes. Okay? Thank you.